So now let's look again at the feasible regions for launch systems. For a given delta V that you need to achieve, using equation 2 from the SPAD book on page 15, which there is equation 1.29. If you give us a value of your delta V that you need and the ISP that your vehicle can perform and the inert mass ratio, and G, of course, is standard free fall. If you put those numbers together, if the ISP you have is smaller than the number on the right, then you have an infeasible condition. So when you do this calculation, ISP must be greater than the term on the right in order to be feasible. And if you use the equality from this equation, and if we put in, say, 9,300 meters per second, then we get this curve here. And that's a curve of a function of inert mass fraction. Okay, we're running that value from 0 to 0.2. So here's where 20% of your vehicle is structure, which is a very high percentage to devote to the materials that are not providing payload and they're not propellant. So everything in this gray area and actually below this upper curve would be not feasible. If we go to a value of delta V a little lower, 8,800, then we get this curve here. That's the 8,800 curve. So depending on what value you want to use for delta V, these are just sort of two practical values. This is the area that you cannot use for a single stage into orbit. So here we have, again, here's the minimum specific impulse that you need in order to be right on the line of the feasible, infeasible cases. So we set this equal, and we put in delta V, say, of 8,800 meters per second. We put in the standard G, which is a number that's defined, and then we put in values of F inert, which is the value on this axis, and out comes ISP on this axis. Okay. So it's ISP as a function of F inert. And then anything in the gray area is not feasible for one stage. Notice that there are actually, interestingly, two values here that are above the curve. And so let's look at those values. This one here is a little bit over 0.3 and a little under 300 for ISP. And if we look at this chart of actual rockets and looking down here to find the 0.03, it's in fact 0.033, and ISP of 281. That's the Titan II. So this is a very low mass fraction, and it's this case right there. That's the Titan II. We have another case that's a single stage can get into orbit, and that's up here. It's got a mass fraction of a little over, around 0.9, maybe a little less, and then an ISP greater than 400. So if we look at that case of an ISP of 400 on these actual values, the value of 400 is right here, 409, and here is just slightly under 0.09 or 9%. That case is the Ariane H150. The other case was the Titan II. So this case here goes right up here. And so we have these two actual vehicles that could get into orbit by themselves. All the others cannot. Now let's look at practical values from real rockets of how the inert mass fraction, F inert, varies with propellant density. And as we said in the beginning with the Saturn V, the propellant density was the reason that kerosene LOX was chosen because it was more dense, much more dense than hydrogen, making the first stage much smaller and therefore manageable, although still gigantic size. So here we have a plot that shows actual launch vehicles. And here's the average propellant density in kilograms per cubic meter along the horizontal axis. And the vertical axis we have the inert mass fractions. And so you see some values up here above 0.07, 0.08, approaching 0.1. And in fact, here's that one case that we talked about with the Titan II that was only about 0.033, a very low mass fraction, inert mass fraction. We also see that the hydrogen LOX is hovering around the 200 here, and we see that the kerosene, RP1 is kerosene, is hovering around 1,000. So that's how we get approximately a 5-to-1 ratio, maybe a little less than 5-to-1 if we go up to here, of course. But just taking roughly the 5-to-1 gives us a dramatic idea of that density ratio and how important it is in the size of your propellant tanks. Now let's look a little further at some single stage to orbit examples. And so here are some inert mass fractions that go with some particular vehicles burning either liquid hydrogen, liquid oxygen, kerosene, hydrazine, and nitrogen tetroxide, and solids. So we have values that range from 0.035 all the way up to 0.08 for our inert mass fraction, which again is a crucial number in designing rockets. It's how much material goes into the structure, to the tanks, to the nozzles, and is mass that is not propellant or payload. Everything that's not propellant or payload is part of the inertial mass. So let's compute some single stage to orbit examples, or go over the computations done in the SPAD book, although I highly recommend doing the computations to understand the details here. We're going to pick as the input. Now let me label for you what are the inputs here. Here's an input. You need the delta V to even get started, right? And you put that into the rocket equation. And then you need an input of the specific impulse. Okay, so here's the hydrogen LOX case. Let's just look at this column and see what the numbers are telling us. And before you go any further, you should go down here and check the minimum feasible ISP, okay, from equation 1.29 of SPAD. And when you do that calculation, you find out this value is 354, and the ISP that we have is greater than that, and therefore hydrogen LOX for 9,000 for the mass fraction, which we also need the input on to do the calculation, is a feasible case. 410 is bigger than this minimum ISP that we calculated in the feasible condition equation. So 410 being bigger than that means, okay, this checks out. We can continue with our calculations. And so we use these equations, the propellant mass equation, equation 1.27 in SPAD, the inert mass equation, 1.24, and the final mass, 1.25, then the initial mass, which is the total. And so we get this number. And by the way, remember that in the SPAD book, they're using 1 kilogram as the payload. And that just makes their numbers easy. I like to multiply by 1,000 to give kind of a more practical value. So when if you had 1,000 kilogram, then the initial mass would be 29,000 kilograms here. So you just multiply by the mass of the payload. And then you can look at the mass of the payload to the initial mass. So we have 1 kilogram here to 29, and that's a little more than 3% is payload in this single stage to orbit. If you look at the hydrazine nitrogen tetroxide propellant, what you get is a much smaller percentage. Less than 1% of that vehicle is payload. So it's not a very efficient case.